Vector databases emerge from a simple but profound shift in how we represent information in modern AI systems. Traditional databases were designed for structured records, clear schemas, and exact lookups. You query by a primary key, filter by indexed columns, and retrieve rows that match explicit conditions. This model works extremely well for transactional systems, financial records, inventory management, and user accounts. However, it begins to break down when we try to search by meaning instead of by exact value. Modern AI systems frequently operate on unstructured data such as text, images, audio, and video. These forms of data do not naturally fit into rigid tables. A paragraph does not have a single canonical key that captures its meaning. An image cannot be efficiently retrieved by exact string comparison. What we need instead is a way to represent meaning numerically so that similar items are located near each other in some structured space. That representation is what we call an embedding. An embedding is a vector, essentially a long list of numbers, produced by a machine learning model. A text embedding model takes a sentence or document and converts it into a numerical representation. An image embedding model does the same for pictures. The goal is that semantically similar inputs produce numerically similar vectors. Two product descriptions about running shoes should be mapped to vectors that are close to each other. Two images of cats should occupy nearby regions of the embedding space. The embedding model compresses complex structure into geometry. Once we represent data as vectors, the retrieval problem becomes geometric. Instead of asking for exact matches, we ask which stored vectors are closest to a query vector. This is called similarity search or nearest neighbor search. Given a query embedding, we want to find the embeddings in our database that are most similar according to some distance or similarity measure. In small systems, similarity search can be done in a straightforward way. If we store 10,000 vectors, we can compare the query vector against each stored vector and compute a similarity score. We then sort the results and return the top matches. This brute force approach guarantees correctness, but it does not scale well. When the dataset grows to millions or billions of vectors, comparing against every vector becomes computationally expensive and too slow for real-time applications. Vector databases are specialized systems designed to solve this scaling problem. They provide efficient storage, indexing, and retrieval for high-dimensional vectors. Their central innovation lies in approximate nearest neighbor algorithms. Instead of exhaustively comparing the query to every stored vector, they use clever indexing structures to narrow down the search space. The idea of approximation is important. In most AI applications, we do not need mathematically perfect nearest neighbors. We need results that are very likely to be among the closest. Because embeddings themselves are approximations of meaning, a small deviation in retrieval accuracy is usually acceptable. By relaxing the requirement for exactness, we gain dramatic improvements in speed and scalability. One common indexing strategy uses graph-based structures. In this approach, vectors are connected to other vectors that are nearby in the embedding space. The result is a network where each node represents a vector and edges connected to similar vectors. When a query arrives, the search algorithm starts at a particular entry point and navigates through the graph by repeatedly moving to neighboring vectors that are closer to the query. This process continues until no closer neighbor can be found. The graph is structured so that it is easy to traverse large regions quickly and then zoom into local neighborhoods efficiently. Another indexing strategy relies on clustering. Vectors are grouped into clusters based on similarity. Each cluster has a representative center. During search, the system first identifies clusters whose centers are closest to the query vector. It then restricts detailed comparisons to vectors within those clusters. By avoiding comparisons with vectors in distant clusters, the system reduces computation significantly. A different family of approaches uses hashing techniques designed specifically for similarity search. These methods map vectors into buckets in such a way that similar vectors are likely to land in the same or nearby buckets. At query time, the system only needs to examine vectors within relevant buckets rather than scanning the entire dataset. This approach can be highly efficient but requires careful parameter tuning. All of these indexing strategies share a common purpose: reduce the number of distance computations required at query time. Distance computation in high-dimensional space is not free. Even though a single calculation is fast, performing it billions of times per second is not feasible in most production systems. Efficient indexing is therefore the core architectural challenge of vector databases. From a systems perspective, storing vectors also introduces unique considerations. Vectors are typically dense arrays of floating point numbers. A single embedding might contain several hundred or several thousand numbers. If each number is stored with high precision, memory consumption grows quickly. When you multiply this by hundreds of millions of entries, memory management becomes a first-order concern. Compression techniques are often used to reduce memory footprint. Some systems store vectors in lower precision formats. Others use quantization techniques that approximate groups of numbers with compact codes. These methods reduce storage requirements and improve cache efficiency, at the cost of introducing small approximation errors. Again, the engineering trade-off is between precision and performance. Dimensionality plays a critical role in similarity search. High-dimensional spaces behave differently from low-dimensional ones. As dimensionality increases, distances between random points tend to become more similar. This phenomenon makes it harder to distinguish truly close neighbors from moderately close ones. Indexing structures must therefore be carefully designed to remain effective in high dimensions. To address this, some systems apply dimensionality reduction techniques before indexing. These methods project vectors into a lower dimensional space while preserving most of the important structure. The reduced vectors are faster to compare and cheaper to store. However, dimensionality reduction must be done carefully to avoid degrading retrieval quality. Vector databases are rarely used in isolation. They are typically part of larger AI architectures. One of the most important integration patterns is retrieval-augmented generation. In this architecture, a language model generates responses not only based on its internal parameters but also by retrieving relevant documents from an external vector database. The query is first converted into an embedding. The vector database retrieves semantically similar documents. These documents are then fed into the language model as context. The result is a system that can access up-to-date or domain-specific knowledge without retraining the model. In this setup, the vector database acts as a form of external memory. The language model provides reasoning and generation capabilities. The vector database provides scalable storage and retrieval of knowledge. Together, they form a hybrid architecture that combines parametric and non-parametric memory. Another common use case is recommendation systems. User behavior and item descriptions are embedded into vectors. Similarity search can then identify items that are close to a user's preference vector. Because embeddings capture complex patterns beyond simple categorical matches, recommendations can be more nuanced and personalized. Metadata filtering is an essential feature in production systems. Each vector is often associated with additional structured information such as timestamps, categories, ownership, or access control tags. A real query might ask for the most similar documents to a given query but only within a certain department or only within the past month. Vector databases therefore support hybrid queries that combine similarity search with traditional filtering. Efficiently combining these two paradigms is non-trivial and requires tight integration between vector indexes and structured data indexes. Distributed architecture is another core consideration. Large-scale vector databases are typically deployed across multiple machines. Vectors are partitioned into shards. When a query arrives, it may need to be processed in parallel across several shards. Each shard returns its top candidates, and a coordinator merges these partial results into a final ranking. Designing this distributed pipeline to minimize latency while maintaining high recall is a complex engineering problem. Consistency and updates present additional challenges. Many vector indexes are optimized for fast search but not for frequent modifications. In dynamic environments where new vectors are constantly added, updated, or deleted, the system must support incremental indexing. Some indexing structures are easier to update than others. The choice of index therefore depends not only on query speed but also on update frequency. Monitoring and evaluation are critical in similarity search systems. Because search is approximate, You must measure recall, latency, and resource usage continuously. Recall measures how often the approximate search returns the same results as an exact search would have produced. As datasets grow or distributions shift, recall can degrade. Without monitoring, this degradation may go unnoticed. Security considerations are also important. Embeddings may encode sensitive information. Even if raw data is not stored, adversarial techniques can sometimes reconstruct approximate original inputs from embeddings. Therefore, vector databases must implement strong access controls, encryption at rest and in transit, and auditing mechanisms. One conceptual way to think about vector databases is to view them as content-addressable memory systems. Traditional databases are addressable by explicit keys. Vector databases are addressable by meaning. You do not retrieve data because you know its identifier. You retrieve it because it is semantically close to your query. This shift from key-based addressing to similarity-based addressing is fundamental to many modern AI applications. The internal operations of attention mechanisms in neural networks mirror this idea. In attention, a query vector is compared with key vectors, and the most relevant values are retrieved based on similarity. Vector databases externalize this concept into a persistent storage system capable of operating at much larger scale than a single model's internal memory. As you design AI systems, it is important to understand the boundary between model memory and database memory. Storing all knowledge in model parameters requires retraining for updates. Storing knowledge in a vector database allows dynamic updates without retraining but introduces retrieval latency. The optimal architecture depends on your performance requirements, data volatility, and operational constraints. In summary, vector databases and similarity search are central components of modern AI infrastructure. They transform unstructured data into geometric representations, enable efficient retrieval in high-dimensional spaces, and integrate seamlessly with large language models and other neural systems. Their design requires careful attention to indexing strategies, approximation trade-offs, compression, distributed architecture, and monitoring. Understanding these systems at a conceptual and architectural level allows you to build scalable AI solutions that search by meaning rather than by exact match, opening the door to more intelligent and flexible applications.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.